In this lesson, we're going to factor and solve polynomial functions. We've factored and solved quadratics, which is a type of polynomial, but now we're going to expand to polynomials of just about any degree. And we'll start off by talking about a couple new special products. Before we've had a sum of squares, difference of squares, and perfect square trinomial. Just axe that, no sum of squares, just difference of squares. Anyway, so we have a sum of cubes, and that's where you have a cubed plus b cubed will always factor out to be a plus b, so a binomial there, with a squared minus ab plus b squared. And so you'll have this binomial times this trinomial. So here you just have a and b, and then a and b are squared, and in the middle we have ab. The tricky thing can be the signs. What is the pattern on the signs here? Because I noticed that when we do subtraction, a cubed minus b cubed, we get a minus b, and then a squared plus ab plus b squared. Well, I'm going to give you a little mnemonic here to help you remember. And dealing with these can be a little bit dirty, but we can easily clean it up if we use a little SOAP. S-O-A-P. And this is an acronym where the first sign is the same. S stands for the same as our original sum of cubes. And then the next sign is going to be opposite, so this is plus, that's going to be minus, and then this third sign is always positive. Same applies here. Same, so this is minus, that's minus, opposite, plus minus, and always positive. So if you remember SOAP, it's an easy way to remember how to do that. So an example of the sum of two cubes, or difference of two cubes in action, let's say I have this 8x cubed plus 27. Well, if I were to take the cube root of 8, that's going to give me 2, and the cube root of x cubed is just x. So I'd rewrite this as 2x cubed plus 3 cubed. So we just rewrote this expression. So we know what our a value is, and we know what our b value is. So then we just substitute them into our pattern here. So a plus b, and then a squared, so that's going to be a squared minus a times b, so 2x times 3, and then plus b squared. So a plus b. So that's how that works. Let's look at another example. So let's say I want to factor these polynomials completely. So this first one's a perfect cube, and the second one's a perfect cube, and there's an addition sign, so that means it's going to be a sum of cubes. So I'm going to rewrite this. I'm going to take the cube root of 27, so that's going to be 3, and then the cube root of x cubed is x, so it'll be 3x cubed plus, and then the cube root of 25 is 5. And now we will do the our little pattern here, which was a plus b, and then a squared, and then it's going to be opposite, so minus ab plus b squared. So let's fill that in. So a is 3x plus b, which is 5, and then over here a squared, so it's going to be 3x squared, or 9x squared, minus a times b, so that's going to be 3x times 5, plus b squared, so if b is 5, 5 squared is 25. So when I simplify this a bit further, 3x plus 5, 9x squared minus 15x plus 25. Okay, and that is completely factored. So this next one, first thing I notice is that the first term and the second term are not perfect cubes. So I can't do that. But what I can do is check for greatest common factor, and there is a GCF. What I want to pull out is a negative number because I want this first term to be positive, and it looks like I can pull out a -2, and I can pull out a total of 2d since there's 5 here and 2 there, so it'll be -2 d squared, and then I'll be left with positive d cubed and then minus 125. Okay, so now what's left inside the parentheses is going to be is a difference of cubes. So I have -2d squared, so I'll bring down that GCF, and I will write this as a, so a, and then minus, because it's the same, and then the cube root of 125 is 5, times a squared, so d squared, okay, O, opposite, and a times b, so d times 5, which is 5d, and then finally b squared, so 5 squared, which is 125. Okay, and again, the sign, same, opposite, always positive. Okay, so let's look at another example. Okay, so here we have a polynomial with 4 terms instead of 3. Now this is really going to be easy because if you've been factoring quadratics by factoring by grouping, then we're going to do the same thing here, but it doesn't require the initial a times c or that initial guess and check portion, because since we already have 4 terms, we will just group them together as is. So I can group together the 27 t cubed plus the 45 t squared. I'll make this a plus sign and make sure it's a negative 3t minus 5. And now I'll just start factoring out greatest common factors, GCFs. So it looks like the largest thing I can pull out of here is going to be 9t squared, and that's going to leave me with 3t plus 5. And then here I always want this first term to be positive, so I'm going to factor out a negative, and that's it. There's nothing else, so I'm just a -1, which will leave me with 3t plus 5. And now these both have a 3t plus 5, so we'll bring that down. So we factor that out, and then we're left with 9t squared minus 1. Now be careful, we're not done. We haven't factored this completely. There's nothing we can do with this first binomial, but look at the second binomial. That's a special product right there. That's a difference of squares. Our first term is a perfect square, our second term is a perfect square, and there's a subtraction sign. So I'm going to rewrite this as 3t plus 5 times 3t plus 1 times 3t minus 1. Now it is completely factored. Okay, so sometimes you can, after you find a factor of a larger polynomial, you can factor that factor even more. So let's look at our third example. Okay, so we want to factor these polynomials completely. So a here, we have 10x to the 4th minus 40. So we'll look for GCF first, and there is. We can factor out a 10, and that will leave us with x to the 4th, and then minus 4. Okay, now what we have here is a perfect square binomial, but it may not look like because you're used to seeing an x squared, but really it is. if I rewrite it, this is actually 2x squareds. This is like saying x squared squared minus 4. So since this is x squared squared, we have 2x squareds. And 4 is a perfect square, so we can go ahead and write this as x squared plus 2 times x squared minus 2. Okay, so this is in the form of a quadratic, even though it's not. The same methodologies we use for quadratics can be applied here, and as we'll see, can be applied with b as well. So again, first thing I want to do, check for greatest common factor. So it's going to be, let's see, we can pull out a 3m squared, and I'll be left with m to the 10th plus 18m to the 5th plus 17. And again, this is in the form of a quadratic. If I rewrite it, you can see it a little bit better. So this is like our squared term, except what are we squaring? We're squaring m to the 5th, right? It's m to the 5th squared. And then this would be our non-squared term. That's just going to be 18, and then this is just m to the 5th. So m to the 5th and m to the 5th squared. So, and then we have our constant 17. So it still fits that form of, you know, ax squared plus bx plus c. So this is, except x is going to be m to the 5th, and then x squared is going to be m to the 5th squared. And it takes just a little practice seeing those, but once you do, it becomes a lot easier to factor it. So I have 3m squared, and then I'm going to factor this quadratic formed polynomial. So since I have 2m to the 5ths and no coefficient, I'm going to write m to the 5th here times m to the 5th. Just like if we had an x squared, we'd have an x and an x. And then I'm going to ask myself, what are multiples of 17 that add up to 18? Well, that's going to be pretty easy. It's going to be plus 17 and plus 1. And that's as far as I can go with that. So that is completely factored. Now, the fourth example, it's saying, what are the real number solutions? And basically, we're just going to take this a step further. We're going to factor, and then we're going to solve. So since we're solving, I'm going to go ahead and set this equal to 0 by moving over the 12x cubed and the 16x. So I'll have 2x to the 5th minus 12x cubed plus 16x equals 0. Next, GCF. I can pull out a 2x, which will leave me with x to the 4th minus 12x squared, except it won't be 12, it will be 6. Plus 8 equals 0. Now again, notice that this is in the form of a quadratic. So here's my GCF, but this is like my squared term. What's being squared? Oh, x squared is being squared, x squared squared. And then this is just my x term, and then plus 8 equals 0. So I'm going to look for factors of 8 that add up to negative 6. So I'll have x squared here and an x squared here equals 0. And we'll be left with -4 and -2. Alright, so we ask ourselves, can we factor these any further? And I could factor this x squared minus 4. That's going to leave me with 2x, and then we'll have x, because this is a difference of squares, x plus 2 times x minus 2. And then I can't do anything with this one, x squared minus 2, so I'll leave that one as is. Alright, since we're solving and not just factoring, we need to figure out what x is equal to. So we will use the zero product property and find our solutions. So everywhere there's an x, we need to set that equal to 0. So 2x is equal to 0, and x plus 2 is equal to 0. Because if any of these are equal to 0, then and we're multiplying, then the whole thing is going to equal 0. And then x squared minus 2 equals 0. And so x would equal 0 here, x would equal -2 here, x would equal +2 here, and in this one we have x squared is equal to 2, then we take the square root of both sides, and then we'll be left with x is equal to plus or minus the square root of 2. So, looks like we have 1, 2, 3, 4, 5 solutions here. So we'll use set notation and list them all out. So we'll have 0, -2, +2, the square root of 2, and the negative square root of 2 are all solutions to this polynomial equation. Alright, so anyway, that is how you factor and solve polynomial functions. I'll see you on the flip side.